welcome to the last session. And it's the last lecture or tutorial by Aida as well. So Aida, you can continue.
Yes, so I will I'll say a few things before I go to the problems, just that I kind of intended to share with you. So I introduced earlier how to use regular languages to prove rationality results for this equivalent Hilbert series. One thing to take away is that one can use these regular languages not only for the Hilbert series, but for any generating function you care about. And if you care about rationality results of your preferred generating function. Secondly, I want to say, so in a recent paper with Uwe, we took this step further. We wanted to get rationality results for like Segre product of algebras, infinite dimensional algebras, and tensor product of them. And what happened is that one can create a very nice story in the world of languages. And when we have a Segre product of algebras as defined here, and these are in the notes that I'll share, where are we? Yeah, so we define the Segre product of two languages, which I'm sharing the notes, but I'm not going to go here into details on how we do that, but it's a slightly heavy notation, but natural definition. This Segre product works as the Segre product in algebra, the Segre product of languages. In particular, if we know that we have two algebras that have rational Hilbert series coming from some languages, then this Segre product of the corresponding languages is in bijection with the Segre product algebra, and it gives rationality results for this new bigger algebra. And a similar story for the tensor product, but the story for the tensor product is simpler because for the language, we just need to do a concatenation of the two languages. It's less work for the program. And I want to end this with a part of like, so it looks like there are some deep and natural connections between the worlds of formal language theory and asymptotic algebra. How much can how much can formal languages help us in our study? So we made these big steps, but there are many other steps to be taken. So one can go with other constructions of in algebra and see how they look like in formal language theory, and use the what is known on this side to get results about the objects in algebra. So that's one thing. And the other is, so I mentioned that once you have a finite automaton, you can explicitly compute the generating function. And so here is one example. So which example is this one? Oh yeah, so they are next to each other. So this one here, yeah. They just are showing up next to each other here, but yeah.
Excuse me, sorry, probably I missed the last lecture. Did you explain anything about the finite automata here? What do you mean by automata?
Yeah, so we did that in slightly in lecture 4 and in lecture 3. So
Okay.
finite automaton is a simple machine, like these two machines here, like simple machines that inputs that is represented by directed graphs that input words and outputs, inputs letters and outputs words with certain rules determined by this graph. So for instance, here we have this graph with starting state 1, and we have these directions of of edges labeled by letters in the alphabet. And the way how we get the output, we said, is we start with a starting state. If it is an accepting state, meaning we have these double circles, then we can accept whatever we have there. So here one is a accepting state, so I also can accept epsilon, which is the empty word.
Mhm.
Or I
Okay.
can leave and I have alpha, and then 2 is not accepting, so I have to move on. I have tau, but then I can read as many taus as I want because I have a loop and I accept that. So all the language here coming from this finite automaton is, we said epsilon and alpha tau to the k for k greater or equal to 1.
So graphically, it is not need to be a walk or something. So it can
No,
be
here.
it.
This is another example.
Yeah. Okay. Okay.
Yeah, so it's a directed graph. So there is a definition of deterministic and non-deterministic, but I'm not going in that. Yeah, if anyone is interested, they can go deeper, but yeah, it's just a directed graph with labeled edges, and some of the nodes have double circles to mean that they are accepting nodes, and one node is a starting node. Yes, so given a finite automaton as like this one, and given some weight function rho, so finite automaton means we have a language L and some weight function rho, we can compute the generating function using the automaton, and here is the formula. So the formula is, it's so for each letter A in the alphabet, we take the adjacent matrix MA, which is yeah, so the entry ij of this matrix is 1 when there is a transition labeled A from J to I. And so yeah, we'll have this in detail here, but so this is what MA is. Rho of weight, then we'll multiply this by the weight of A, and then we take the sum over all these adjacent matrices. Then we subtract this sum to the identity matrix. R is the number of states, just the dimension of this matrix here. So we have now this we have now this big R by R matrix here. We take the inverse of that R by R matrix. Claim is that it's like invertible. And then, so yeah, so we have so this is here, this is an R by R. And then we multiply to the right by this E1, which is an R by 1. And this ends up being an R by 1. But then we multiply to the left by a 1 by R. 1 by R vector. So it gives us 1 by 1. So where this vector U is the indicator vector for the accepting states. For instance, in this case, it's going to be 1, 0, 1, because the 1 and 3 are accepting states and 2 is not. And E1 is just the kind of the indicator for the starting state, so it's always this one, E1. So yeah, and now this becomes very, very linear algebra. For instance, so in that example there, we see that for tau, sorry, for alpha, we have this M of alpha. We have only 1, 1 here in the position 2, 1, because there is like this edge 1 to 2 indicated by alpha. And for M tau is this one, we have 2 1s here in position 1, 3 and 2, 3. Sorry, 2, 3 and 3, 3, because 2, 3 and 3, 3 is the loop. And then we multiply by the, why is this doing this to me? We multiply by the weights of each of these letters. and we subtract it to the identity, and we multiply, as I said, by these vectors, and we get a 1-by-1 matrix, which is just this. That's the entry of that matrix at the end, and that's our generating function. So the kind of takeaway of this is, once you have the finite automaton, you are done with getting the rational presentation. And if somebody asked me the other time, what is a good reference? Here is a good reference on all these related questions on formal languages and automata. Okay, and then, so I told this. Okay. Then we go to the problem sets. So here in problem 37, I've asked if here there are two finite automata. Describe how the words coming from that automata look like, and given this weight function, compute the generating function for them. I claim both of them represent nice algebraic objects, but so that's the kind of the question here. And yeah, what you would need to do here is just, so in the first part, we start with at 1. So what are some possible words we get out of the first one? Maybe someone can make guesses, can tell me, oh, one word in this language is this one. So epsilon is there because this one is accepting state. What else? What is a word we get out of this first automaton?
Of 1
We
to
can
the
read
n.
the top. Sorry?
Alpha 1 to the n, for example.
Alpha 1?
The power of n.
Oh, yeah, alpha 1, but n should be, alpha 1 to the n, yes. Because like you go here and you read alpha 1 again and again and again. Yes. There are many words that come from here, in fact. The only words that are not accepted, what is something that we see, oh, this is not accepted here. If you read an alpha 2, you cannot read an alpha 1 after alpha 2. You can read another alpha 2, you can read a tau, but you cannot read another alpha 1. So you don't have alpha 2, alpha 1 here, not allowed. So alpha 2 is always either followed by an alpha 2 or a tau. Okay, and I claim this, this represents this, I think, how many? X 2 by n. Okay, and similarly for this one, and these will end up with like incidence matrices that are 3 by 3 and so on. And in problem 38 is, this is more involved because with Uwe we have a conjecture in our paper, prove that this is the right answer. And so what this does is this is trying to solve this problem here. If we take this this algebra to compute the equivalent Hilbert series, and the conjecture that it looks like this. And what this is asking is to check that the language I represent here is the right language for what we are trying to solve, and the finite automata is described here. And so this asks to finish the linear algebra steps. So let me know if you have any questions, but I'm gonna just explain this first in step by step. And and this one is take the ideal generated by the 2 by 2 minors of this matrix, and then you create a filtration this way. Is this finite? And provide a finite generating set, write down the associated monomial algebra, so because this is a toric ideal, and is the algebra finite, and to compute the rational equivariant Hilbert series if it is rational. And the problem 40 is telling about a generalization of 39. So this is like the the Veronese embedding, and this is to compute the equivalent Hilbert series of the Veronese embedding, to this Veronese embedding. And one can generalize this to like higher dimensional or the Segre Veronese embedding, and these are all open questions that people have not tried. And this is something I already mentioned, a comment on like extending the vocabulary between formal languages theory and or dictionary and asymptotic algebra. And the last part, problem 42, is so we suspect that the equivariant Hilbert series is not rational when we are in polynomial rings that are not in the form x c by n. And in particular, like we suspect that the polynomial ring itself, x m by n, does not have a rational equivariant Hilbert series. So trying to prove that. So yeah, all of the last parts, all of them are like either open questions from 39 below, or here is a conjecture given already. Yeah. So if you have a question, more specific question on like, what would you like me to say about any of these problems? Tell me. Do you want me to share on the Zoom the problems? I did send a file via email.
It is uploaded on the website.
Okay. Yeah, so the answer to this one is already in the paper with Uwe, to this first one. The second one, I do have the answer, but not in the paper. So if you want to check, I can tell you the answer. And yeah, problem 38, I already have given you some computations for cases when c equal to 2. And this is already I've done a lot of computations for greater and then c greater than 2, and it's what I'm sharing here. So one needs to prove that for any c, that's the answer you get. You can also, you can try yourself and check if your answer matches what I'm sharing. For 39, there are many ways, I think, not only with the regular languages, how you can go for 39. If you don't want to use regular languages, you can just go with trying to compute monomials, either go to with ideal, go to Grobner basis and leading term ideal, or with the algebra itself, or try to construct a formal language. I myself am very interested on 39 and 40 to know the answer, but I have not done the computations, and I don't. I do think there are many ways how to approach for it, and probably the formulas are nice. Yeah. But one would need to finish one and two to be more comfortable with this type of problems. Okay, any questions? So maybe, yeah, maybe some students try the first problem because it's like 3x3 matrices. So I don't think it's that bad. It's not bad at all. So what are the incidence matrices? M of alpha 1, M of alpha 2, and M of tau. So what is M of alpha 1? It's a 3x3. It's going to be 0. And now from 2 to 1, we have 0. So the only alpha 1s that we see are this one and this one. So we will have 2 1s. We will have in position 2 1, a 1, in position 2 2. And then similarly with the other one, M of alpha 2, we have alpha 2, alpha 2, alpha 2. So we have 3 of them. So we have 3 1. Okay, so we have a 1 here. We have 3 3. And we have 3.
Last row.
Yes. Yeah. And with tau, we have 1 tau here, 1 tau here, 1 tau here. So what do we have? 1. Yes. So we have 1, 2 1, 3 1. And yeah. And then you multiply this one by what? Tau of alpha 1 is S1. Sorry, it's T. T, E, S. You take the sum, you subtract it from the identity. And what do you get? So when you, it's going to be 1 minus S. And then it's going to be
Minus S.
because of this. Oh, yes, minus S. Thank you.
Next one.
Yes. Minus S, minus
Minus
S. And
S.
then
And
we
minus T, 0.
1 minus T here.
Oh, sorry. Yeah.
And then
And then
T,
minus T and 1 minus T.
and then you take the inverse of this matrix.
Mm.
And then you multiply here by 0,
1,
0.
0, 0.
And then you multiply here by, so all of these are accepting states. So it's 1, 1, 1. And you can put this if you want in Wolfram alpha, whatever, in like, if you don't want to do this by hand, and you get the answer. So the answer is a rational function. Or you can do it by hand, but yeah. So that's how you do, and that's how you would go for the other one. The other one has only one accepting state. So this vector, the first one, will be 0, 0, 1. So does that make sense? Does that sound like looks like scary anymore? I hope not. Like the part of computing the rational form, it's not. I think that's the friendliest part of all these problems. So the main kind of challenge is to prove the bijection between like the algebraic object and the language we are constructing. Kind of to find the conditions that make the mapping a bijection. Okay. And so maybe here, yeah. So here I've given one automaton. So what are the possible outputs of this one? And I claim all the possible outputs look like this L here, where where I1 through ID are, in this case, are alpha 0, alpha 1, alpha 2. And the reason why they are written this way in here is just to say that we have every finite automaton that comes from our problem arrives as like one can write it as a finite set of inequalities given by a finite set of inequalities. Like the word finite is very important. Finite set of conditions on the words. Okay. Okay, so if anyone has the answers to part B of 37, shut them out. Or if I also welcome any suggestions on what part do we would like to focus more.
Could you please explain how we extract these matrices from the graph?
Yes. Yes, so the rule was for each letter, let's I'm gonna clean this up.
दो ही हैं शायद.
So I'm gonna work with this other here. So okay. So the matrix, so in this case we have 4 vertices and we have these letters alpha 0, alpha 1 and tau. So for each letter we have an incidence matrix for that letter. So let's say I'm gonna take M of let's say alpha 1, and this will be a 4 by 4, where 4 is the number of nodes, and we have that M alpha 1 of ij is 1 if there is a from j to I with alpha 1 label. If there is an edge from j to I with a label alpha 1. Otherwise is 0. So in this case, what are the entries that are 1 for M alpha 1?
Is going to be 3, 2 or 3, 1?
It's going to be the entry.
1,
So
3.
ij, j to I. So kind of flipped. So we have this from 1 to 3 and from 2 to 3. So from 1 to 3, that means 3, 1. 3, 1. 1, 2. So then 1, 2, 3, 4. So this one will be 1. And from 2, yeah, so from J I'm not wrong. Yeah. So J to I. So 3, 1, yes. And 1 IJ. 2, 3, yeah. And 3, 2. I have 1. And everything else is here. Yeah. So maybe one computes what is M of tau. M of tau in that case is going to be what? The tau appears here. Here, 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 and
One,
here.
1,
1,
1, 0.
So we are saying it's in, I don't,
1, 1, 1, 0. First row.
1, 1, 1. We don't have space for it. So M of tau is, we're saying 1, 1, 1,
0.
0, because they are,
Second row is 0.
mhm,
And then third
0.
row.
What is the third
Uh,
one?
There is 0, 0. Last one is 4, 1.
Because of from 3 to 1.
Sorry.
It's 3,
Yeah.
3 is here. Yeah, but we have 3 to 4.
No. Not zeros.
So with the 2, we have from
0, 0, and 0.
for this one,
Yeah, it's a 0 row again.
okay,
And the
and
last one is 1, 1,
mhm,
and 1, 1, 0.
mhm. Yes,
0.
yes, because we have the 3, 4. So there are exactly 6, 3 and 3, 6. And the ones that relate to, like they are coming to the entering 1,
1,
the ones that are entering 4.
2, 1, 2, 3, and 7. Yeah.
Okay. And so the same thing for alpha 0, and then we multiply each of them. So this one, we have to multiply it by the weight of tau, which is S.
Is
So,
S, yes.
and alpha 1, we should multiply it by the weight of alpha 1, which is T. And then the same for alpha 0, and we take their sum, and we do what I said earlier. So the steps are given here. This is the formula. Yes. Is that clear now? To the person that asked the question.
yes.
Okay. Could you let us know about M of alpha 0? What is M of alpha 0?
So it will be 1 at the indices second row, second row, first column, 1 otherwise 0.
Yes, so there is only one alpha here in the position 2, 1. Yes. And everything else here. Yeah. And we multiply it by what? And so I've not told you. So the row of alpha i's is always S. Oh, I did the opposite here. I meant the opposite here, honestly. I'm gonna change it. It's not that it matters that much. You still can do computations, but I meant this one here. So this is gonna be T. Just to make sense for the algebra, but the weight does not matter. Like the rationality result does not matter on the weight, as long as it comes from an automaton. And then you take the sum of all this, and you take the inverse, and you multiply by the identity the standard vectors in this case, and you get the answer. Okay. And something that, yeah, I have written the notes, but I did not explicitly said in the lectures. I'm not explaining what the star here means, but the star, yeah, here it's the star. So if we have an alpha and we write star, we mean this contains all alpha to the k for k greater or equal to 1. And it's called the cleanest star. And something about the regular languages is that they are outputs of the finite automata, but they are also can be constructed in like very recursively in the following way. You like start with like the languages that contain only one letter. By definition, we call them regular. And then the concatenation of any regular languages is regular. The union of any two regular languages is regular. And this clean star is also regular. And with these operations, doing these operations onto the one letter languages, you get all the regular languages. So all the regular languages can be expressed as written by these operations. And that's kind of, that is what part A is saying here, that, oh, all these words here, blah, 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 they can be rewritten in this form. Maybe I should remove this. They can be rewritten as oh, you have all the singletons or concatenation of some of them. And then you, when we have a set, means you choose any of these words. So it's union. You take the cleanest star, and you again can read one of the just singleton letters, and then you do a cleanest star to tau. And this description here is the same as output of this automaton, and that's the same as this one here. And some folks prepare this writing as in part here with these operations. The only problem is that this has disadvantages in computing the rationality, and sometimes it's easier to come up with automaton than to come up with the this expression. Yeah. Okay. So maybe if we understood like the construction, maybe one can check if in this automaton here, if you do I of 1, 2, 3, 4, 5, 6, I6 minus the sum of all this row of alpha i's, m alpha i's, minus row of t, m of t, tau, row of tau, m of tau, if this expression as all is the same as this expression here that I wrote.
In this automata, you are taking double indexing. So does this choice of indexing depends upon on which polynomial ring we are dealing with, like with n cross n or n cross n cross n or so on, or what is?
That's a very, very good question. The double indexing, not necessary. So in this case, we have double indexing because, so we are not, yeah, we are only having one direction growth, but somehow in the proof, the rules, they arrive in a way that we can write them in terms of the indexing, but not really.
Okay.
Not necessary. Not necessary. That's the word.
Thank you.
Not necessary. Yeah. Sometimes they do. Sometimes it's good, it's useful. In this case, it's only one direction, but I've done double indexing because it's easier to write down the rules in like with words. But I will say this, okay, maybe something about the indexing. Okay, that came like in a good direction of the conversation. So the double indexing here may have to do with how many generators we have in our case. So this was for c equal to 2. So we had like, so we had alpha 0, alpha 1, and alpha 2. So alpha 0 corresponding to this x0 square, all good. And then the ones that really kind of set more kind of things to take care of were alpha 1 and alpha 2, and there were two of them, and they set up this kind of double indexing. They made us to do double indexing. So I would say, yeah, especially from the paper we did with the Segre product, the indexing, if we take an arrow versus like just counting 1 through and so on, depends on the number of, sometimes also on the number of generators. Minimal number of generators up to the action.
Okay.
Yeah. Okay. So is anyone trying 39? How do the generators look like? So there are kind of two types there. There are the ones that are square free, and there are the ones that have a square showing up. There are of the form, so we have x1, x3 minus x2 square, or x1, x4 minus x2, x3. How do we write them? Maybe in a finite way. And whenever we stop somewhere, we can call that, like, say, if I stop here, then I take this one and I call this as I3. If I stop here, I call this I4, the 2 by 2 minor, and so on. And so I have this IN for n in n. And how does that look like? And for part B, maybe problem 40 is also useful. Because it's not that straightforward. Also, if you want to ask any questions about the problems that we had done earlier, you can also ask. But a problem that I would, highly, highly, strongly encourage to also try is problem 40. Which relates to problem 39. But I have been thinking, I have thought for a while I have thought many times, I'm like, oh, I need to solve that. Somebody needs to solve that. I need to solve that. So, and I have not had the time, but I think that's a very, very good problem. Very good open problem. Because there are like, in algebra, for me, there are two very fundamental objects, is the ideals of the Segre products and the ideals of the Veronese embedding and then you have the combination of them, Segre Veronese, but one step at a time. So this is suggesting to do Veronese embedding.
So you are saying here 42, problem number 42 is an open problem.
Problem 40.
Problem 40.
Yeah, all of them are open problems. And I'm saying, I'm saying 39 and 40 relate with each other. And I'm saying they are open problems, and I'm saying I'm very kind of, I'm advocating for them a lot.
Okay. Okay.
That's
But okay, I think so I'm missing something. Maybe I would like to clear that one, because when you gave an example in the previous lecture, you said that this is an example of n cross times n cross.
yeah, like this
And
one.
yes, that like this one, and that you have done in your
We-
paper.
Hmm.
But you done for the monomials, particular monomial algebra, or
So what we did there was not computing this. We did not compute this. What we
Okay.
did there, we computed within this ring, we computed the Segre algebra.
okay, that's why monomial. That
But-
was the associated monomial algebra.
Yes, yes. But
Okay.
but the algebra generated by, so if we take just the algebra generated by all these xij's,
IJs, yeah.
for every I and j, this is not
This
solved.
is not solved.
Even though
Okay.
it looks like
So what you have done,
monstrous-
so let me just what you have done, that is xi squared and xi plus 1, right?
The one I mentioned here is also this one, is the k of xi times also this is n by n. Xi plus 1.
Here, yeah, and xii plus 1.
Yeah.
Okay. Mhm.
Related to this, it was also not in the algebra sense, but in the ideal sense, it was like
Mhm.
all the 2 by 2 minors
Mm.
of x n by n,
Yes.
for instance.
Mhm.
But not all the ring itself. So the ideal of like the zero ideal, we don't know. Take the zero, which is silly. But somehow it's the suspicion is that it's not rational. If we take the 2 by 2 minors, we have a very nice formula, the one I gave. If we work in the algebra kind of world on this setting, then in the algebra work, I have never worked in this setting. The ideal lives in this setting. The algebra translates in like all these xi, yj's, or xi plus 1, stuff like that. So it's not exactly this. It's like, sometimes it's like xn, yn. But if you take the ideal, the zero ideal, in this polynomial ring, we don't know if the Hilbert series is rational, the equivariant Hilbert series. Yeah. But the formula is very like, yeah, where does someone start? I do have some notes on this part. If anyone is interested, I can share those notes. But so yeah, basically it's, you have this R n1 and 2, which is R of X n1 and 2. And then, so this one has Hilbert series, which is 1 over 1 minus t to the n1 times n2, as I said earlier. And then, because you take the sum over every n1 and n2. And s1 to the n1, s2 to the n2. And to prove that this sum is rational or not. The suspicion is that it's not rational. So probably like trying to rewrite this as something that depends on a sum that we already know that is not rational. Yeah, there are some gamma functions that arrive from physics that look like similar to this. But yeah, so the point is to prove, yeah, this problem is the same as show that this sum is not rational. Yeah. I don't know how it's, so how difficult or not difficult it is. It's not straightforward, but also I don't know if it's very difficult. If someone has the right knowledge on this, then they just solve it maybe very, very quick. But there is, yeah, if this is solved, then this is the first example that is not proven to not be rational. And it's like, yeah, amazing, right?
And even it is not clear in the problem 40 about the kernel of that map.
For which one? For problem
Number 40.
No, that one I think that's it's irrational. I just it's just not
Okay.
been worked. This should be just n like this here, but yes. No, I think that's like problem 40. I think it's it can be worked out very nicely. So yeah, it's just I think it's a very good class to work on. And they are kind of fundamental objects to work with, but yeah, I do suspect it's fine. Problem 40, I think is all fine. Just needs someone to kind of decide to work on it, and it's gonna be solved. That's my yeah.
In the above problem, we are considering the ideals generated by the 2x2 minors.
Yeah.
So the generating set will be I4 only. The whole set can be generated by the same orbit of I4.
I4.
Yes.
Yes, I suspect that too. So up to what? How did you decide the group action?
Yeah, group action is acting on the indices.
Yes.
And one more thing I would like to ask is that we are considering the S infinity.
Yes.
But in this case, only the inc operator also suffices this condition. So why do we need the S infinity operator?
No, I wrote S infinity because I only talked about S infinity throughout the lectures. You can use the inc operator. Highly encouraged, whatever works.
In yesterday's lecture, I attempted those problems where we have to compute the hierarchical ideals. And those ideals are finitely generated up to symmetry if we consider the inc operator.
If you consider the inc operator, you're
so
saying?
I sent you the email and you replied to me.
Oh, yeah. Uh-huh.
So in first two problem A and B, so the generating set is finite, but not the third one.
Here.
Yeah, this one.
Yes. Yes, they are finite. What is a finite generator? Yeah, the first two are finite. Yeah, and the third one is not. But the thing is that the third one is not, but you can write the generators. y- Not in a
Uh,
finite way, but there is you can do a combinatorial way to write the generators.
when I try to compute these ideals, so these ideals generators grows exponentially. So in
Yeah.
the second case, I'm getting something like 4,000 generators.
Yeah, so I'm gonna give you the answer what happens with C. C is gonna be like that. It's like it grows exponentially. There is no finiteness. There is some structure though, and the structure is in the following. So if you take an element in the kernel, it will look like this. It's gonna be X. So what was this? The first one was a 2? Yes. So I fixed the first one. So here this was for this one. 2 and 1 and 2. So this is gonna be X, 1. Let me go. Okay. I1, J1, X1, I1, J2, X1. I hope I remember well, yeah. I2, J1. J2, sorry. I2, J2, till 2, X1, I, K, JK, and X1. I should have an, okay, I think it's too many indices here, so maybe that's not a, I gave you a reference that kind of gave the hint on how the generators look like in the last case, but they grow exponentially, but there is a pattern on the indices that runs through cycles. That's what I was trying to do there, but I don't have the generators in my hand right now, so should look at the notes. 1, 2, 1. What is this one? Okay, so 2, 2, 3, 3, 4, 4. So basically, I'm gonna give this hint, because writing them down is like, as you said, the generators, the degree grows exponentially, so it becomes a lot. But so 1, 2, 3, n, 1, 2, 3, n. If you take any, so there is a bijection between the cycles you take here. So that's my hint. Bijection between the cycles here in this complete bipartite graph, and generators in I and 2 and n. That's so all what I'm trying to say is for the C is also, it's not finite. There is combinatorics going on that
one. Okay. Also, could you please give insight about the part A, where you ask the provider conjecture for IR? So when I try to compute these ideals, so I see that the ideal set does not contains in each other's.
The ideals are contained, definitely.
For example, the ideal
Oh,
I2
these were not. These are not, because like
yeah,
contained only when all the numbers are less or equal. Yes.
yes,
This
yes,
is a grid. It's not a chain. Yes.
yes, exactly.
Yeah, so we did give the answer to A. The answer to A was that you only need to compute this here, and the rest is obtained by applying symmetry group actions in each of the indices, not only in one S, like not the same as everywhere, the same as infinity. So the conjecture is that, if you want to know, I can also write it down. This one I can write it down because it's only one generator. So the conjecture is that I of R1 or of N1, N2, and 3 is S infinity times S infinity times S infinity of X 1, 1, 1, X 2, 1, 2 minus X 1, 1, 2, X 2, 1, 1. That's what the answer is. So I claim in all the answers you had in each of these cases, the generators were obtained by taking this one and applying symmetries in each of the indices.
This is the pattern I got too.
Yeah, and this is also what we said in the lecture, that when we have a, so this delta here is decomposable. So by Dobra, we do have finiteness, and it arrives when all these numbers are 2. Like, or earlier, but at least when all the numbers are 2. Yeah. And something similar here. Also here, this I22 gives everything up to sim.
Thank you. Thank you.
Yeah. Yeah. And here, yeah, this like n when I say, yeah, so this is, yeah, I don't know how much I want to go to. Yeah, so it's like x1, I1, I2. So if you take, or let me take this cycle here and call it a day because it becomes work. So x1, 1, 1, y, or we don't have y, x2, 1, 2, x1, so 1, we go here, and then we got 1, 2, we got here, and then we got with 2, 3, 2, 3, x2, so we use this one, 3, 3, and x1, 3, 2, and x2, where are we? 3, 2, yeah, 1, 2, minus, we take all this expression, but we exchange the first with the opposite. So it's like x2, 1, 1, x1, 1, 2, and so on times same x1, 1. Oh, this should be 2, 1 here. And this is x1, 1, 2, 1, 1, 1, 1, 2. So yeah, so there is some pattern for the last one. In fact, the last one is called Lorentz lifting of the 2x2 minors. So there, yeah, there is a lot of beautiful combinatorics.
Okay. Is there any
Like
question or something?
Yeah.
Or is it time to end the session?
So the last one, I will say also this, like in the paper I mentioned here with like a collaborator of mine, Taylor, we do use these combinatorics, these graph representations to compute the degrees of these ideals and the maximum likelihood degrees. So even though there is no finiteness up to symmetry, there is some kind of structure how we, yeah, that we can take advantage of. Okay, any other questions?
Is there any other question from IBA or from here, the audience?
If there is no question, so let's thank Aida for very nice and informative talks and lecture series. So it's a really great honor to have you here, still online, but still
I'm
online,
very
but still we are enjoyed your lectures, tutorials.
Thank you. I had a lot of fun. I hope. I'm sorry. I apologize. I was not there. I will. Yeah. If you have any questions regarding these lectures, regarding especially the problem sets, and you are trying one of the or more than one of the open problems, and you want to maybe discuss about them on the progress or anything, you are very highly encouraged to email me.
Yeah,
Yeah,
sure, sure,
you
sure.
all have my email, so it's all good.
Yes. So,
yeah.
participant, listen, if you have any question or anything related to the Aida's lectures or problems, you may write her directly
Yes.
to ask any question, right?
Yes.
And okay, that's it for the today's session. And now we have this is the like second last day of the Simba school, and tomorrow is the last day. But let's thank Aida again for making these at very odd time. But I hope so everything is going well at your side when you are doing these lectures. Yeah, okay, that's great.
Okay.
So thank you again.
Thank you for all the questions. I really enjoyed that part.
Okay, that's
Because
great.
as always, like the when people ask, that means they are listening.
Yes.
Or-
Yes. That